Yeah, hello. Good morning, everyone. Hello, am I audible?
Yes, sir.
Yes, sir.
Okay. So we'll wait for a few more minutes, then we'll start. Yeah. Do you have any doubt in week 5, week 6 content? Anyone?
Yes, sir.
Hello?
Hello.
Yes, yes.
Yes, sir. In week 6,
Week 6. Which part?
sir. Checking for BCNF.
Okay. So, what you didn't understand? Any condition or what?
Sir, I didn't get it. Whether do we need to do it from R2 and then check to BCNF, or directly, like if it's not a candidate key, then we go directly to convert that to a BCNF.
Right. Sorry, I didn't get your question. Like, to check the BCNF condition or to decompose the table in BCNF. Like, that's what you are asking, right?
Yes, sir. Do we need to first check for 2NF, 3NF, and
Yes, yes.
then do it, or can we just say if the functional dependencies doesn't contain a candidate key, we can directly decompose that to BCNF, or how that should be done? I have a confusion with that, sir.
Okay, just one.
Yeah, I think more generally for me as an extension is the process of decomposition. I mean, process of checking whether it's BSNF, BCNF, 2NF, I think that is reasonably clear. But the process of decomposition is not that very clear. Yeah.
Yeah. Okay, so we can take one practice question and we can try to decompose one relation into 1NF, 2NF, 3NF, and then BCNF, right? That will be good. We can decompose till BCNF, right?
Yeah, sure.
Yeah. So today we are planning to take a summary session for normalization concept. So Professor Nirav is going to take that, but till he join, we can discuss that question. Yeah, so I will be taking question number 10 from practice assignment, week 6. That is the question. Yeah. Yeah, so is my screen is visible here? Question number 10 here you can see, right?
Yes, sir.
Yeah, so we have to we have to identify the given decomposition, but we'll not go through the option. We'll simply decompose this relation R into BCNF. Okay. Okay, so what is the first step here? First step is to find out the candidate key of a relation R, right? So what is the candidate key here?
ABH and ABG.
Yeah, so D is present, EF is present, CG is present, H is present. So AB must be a part of candidate key, right? So let us take the closure of AB. So from AB, I will get AB like trivial function dependency. From A, I will get D. From D, I will get EF. And okay. So AB is not a candidate key, right? So let us check for and all the combination like 3 attribute combination like ABC, ABD, then ABE, then ABF, then ABG, then ABH, right? So here if you see, if I take the simple closure of AB, I am getting ABDEF. If I get G here, I can get H, right? So if I take the closure of ABG, like from AB, I will get A, B, D, E, F, and from G, G will be also there, right? And from G, I will get H. So from G, I will get H. So this, all the attributes are present. If I take the closure of ABG, so this must be my relation R, right?
C is not present.
Yeah, C.
Oh, from BH you will get C.
Yeah, BH, sorry. From BH, we'll get C, right? Now here, Okay. Now let us take the closure of ABC. Like, do you anyone get it? Like, why I have considered directly ABG here? Because I take the closure of AB already, right? But if I take add G here, I will get all the attributes.
Yes, sir.
Right? Yeah, looking at this only, I can see, okay, C is missing, G is missing, and H is missing. So I can take the closure of ABC, but it is not giving me all the attributes, right? Now I will check for ABG. It is giving me all the attributes. Now I will check for ABH also. From AB, I will get A, B, D, E, F, and H is also there. And from BH, I will get CG, right? So this is giving me all the attributes present in the relation R. So ABG and ABH are two candidate key here, right? So the candidate key of relation R is ABG and ABH. So what are the prime attributes here now? What are the prime attributes? Prime and non-prime attributes?
A, B, G, and H.
Yes. So the prime attribute are A, B, G, and non-prime attribute are C, D, E, F. Right? Yeah. So this is our second step. Now, is our relation is in first enough? Like, where domain of all the attributes consists of atomic values, right? Here you can see the domain of all the attributes consists of atomic values. So we can say our relation R is in first enough, right? Now let us check for second enough. What is the condition for second enough?
No partial dependencies.
Yeah, for second enough, there should be no partial dependencies. Now, how to check that partial dependency? Suppose if I have functional dependency, say X determine A, and X is a prime attribute or subset of a candidate key, and it's determining non-prime attribute. Yes, just 1 minute. Okay. Yeah, sorry. So, yeah. So is my screen is visible, right?
Yes, sir.
Okay, so what is the condition for 2NF? Like there should be no partial dependency. Like if X is determining A and if X is a prime attribute or a part of candidate key and determining non-prime attribute, then we can say there is a partial dependency, right? Now let us check for this functional dependency. Whether A determined is a partial dependency here. Yes, anyone?
Yes, sir.
Yeah, this is a partial dependency. Let us check for D determining EF.
No.
Because D is not a part of candidate key, right? Now let us check for BH determining CG.
It is.
Yes, right. G determining H.
Yes.
Now
But
both
no,
are prime
no,
attributes.
both are
right?
prime. Yeah.
Yeah. So these two conditions are not satisfying our 2NF condition, right? These two functional dependencies. Right. So in order to make this relation R, we need to decompose it. And for decomposing into, sorry, in order to make this relation R into NF, we should remove this partial dependency, right? So how to remove this partial dependency? By decomposing this relation R into R1 and say R2. But how to select like for which attribute will go to R1 and which attribute will go to R2? Because for that we need to remove this functional dependency. So what I will do, I will take the left hand side of this functional dependency, and I will take the closure of that. Right now, if I take the closure of A, what I will get? A, D, right? From D, I will get E, F, right? So any other possibility? No. So I will make this ADEF as a relation R1. Okay. So let us check for this BH also. If I take the closure of BH, what I will get? So B, H, C, G, and from G I will get H, right? So I will make this relation as R2. So our R1 is A, D, E, F. Our R2 is, sorry, R2 is B, H, C, G. Now whether this decomposition is lossless or lossy? Does anyone?
Lossy, because there's no intersection.
No intersection, right? So we make make this decomposition lossless. So what I will do, I can add one more table R3, and I can make any of this key as a one table, right? ABG or ABH here. So which one should I take?
You could take either, right? Or ABH.
ABH
The
or
options
ABH?
is ABH.
No, options ABH, but we can also look for ABG, right?
Yeah, we can, correct.
Yeah. It is not only that only one decomposition is possible, multiple decomposition is also possible, right?
We'll go with ABG just for
yeah,
be different.
we will go for ABG. Yeah. So ABG, right? Now let us see. Okay. If I take the intersection of R1 and R3, I will get A, and from A I will get this R1, right? So this to satisfy my lossless decomposing condition. Now A, B, D, F, B, G, because we need to take the intersection, like say R13 equals to R1 union R3 equals to A, B, D, E, F, G, right? So now if I take this intersection with R2, what I will get? B and G, right? And from BG, I will get, if I take the intersection of R13 and R2, I will get BG, right? And if I take the closure of BG, from BG, I will get, from G, I will get H, and from BH, I will get CG. So that is BGHCG, right? So sorry, G is repeated here. So I will get R2 here. So our decomposition is lossless, right? Any doubt up till now what I have done? Okay.
So just one question. This arriving at R1 ADEF, you have used just AD relation, the functional dependency AD, and from there you have done a closure of A. Is it A plus?
No. We need to remove this partial dependency, right? So these two are partial dependency, right?
Correct.
I am simply taking the closure of left hand side of this attribute or set of attributes.
Okay, the full closure. Okay, but in this case, it just turns out to be ADEF.
Yeah, in this AD, and from DEF, and for BH it is CG, and from G it is H, right? Okay. So I have three relation now: ADEF, BHCG, and ABG. Right. So now, what are the applicable functional dependencies to R1 here, like from the parent functional dependencies? I will take just R1 here, and that is A, D, E, F. What are the applicable functional dependencies here? From this only, A determine D, and D determine EF, right? And for R2, B, H, C, G, right? And applicable functional dependency, like VH determines CG and G determine H, right? So,
sir, I have a doubt in decomposition of R1. Sir, if we take AD functional dependencies, and if we take like R1 is A comma D, and the other R is R minus R1, then how will that turn out?
Okay, so you are asking like I make this R1 and other R2 as R minus
R
R1,
minus,
right?
sir. Yes, sir.
So let's just say R2 will be that remaining attribute, right? So B, C, D, E, G, H, right? Yeah. Like for this case, we are getting the same relation, right? But it may not be possible because we have to remove these partial functional dependencies also, right?
Sir, for just considering A to D functional dependencies, then R1 will be A comma D, and then R2 will be R minus D minus A, no, sir?
Yeah. Then in that case, R2 will be say AD, but rest of the attribute. But that decomposition will be lossy, right? So we need to add one in a common attribute. So we can add A here, right? In R minus R1, we'll get except AD, we'll get all the attributes. But that decomposition will be lossy, right? Either we can add the one of the candidate key, or we can add one attribute A, so that we can make the lossless decomposition, right?
No, sir. After by having R minus R1, there will be no D in that expression. But how can we then eliminate D functional dependency to EF? D to EF. D determines EF.
No, why we need to remove this? Like I just make R1 as AD and R2 as say B, C, E, F, G, H, right? So you are only considering this functional dependency, not the rest of the functional dependency, right? Or only two functional dependency. No. We first need to fix like what are the functional dependencies are given. If you are just considering these two functional dependencies, then I need to take the closure of A, right? In order to remove the partial. So it will be A, D, E, F, right?
Okay.
Yeah.
Okay, sir.
Okay, so R1, R2, and say R3 is our A, B, G. So what are the applicable functional dependencies are here? No one, right? Since it is a candidate key, this already is in BCNF. Okay, it is in BCNF. Already it is in BCNF because if no functional dependence applicable here, the combination of all the attribute is the key here. And already since ABG is the key, it will give us all the attributes. So this relation R3 is in BCNF. Okay, already. Now, okay, so R1, R2, R3 is in 2NF. Okay, till now, any doubt here? Right, so our relation R1, R2, R3 is in 2NF. Now let us see for third NF. So what are the conditions for 3NF? Yes, anyone?
Either X has to be a super key or A has to be a
no transitive dependency. Means if for X determining A, X must be a super key, right?
Correct.
Or no, or in
or
what
A
we can say
A has to be a prime attribute.
Yeah, A as non-prime attribute should not determine non-prime attribute, right? So let us check for R1. So here A is a key for this relation R1. If I take the closure of A, will I get AD? Right?
Sorry, I missed the question. What were you saying?
Like is A is a key here for this relation R1?
Yeah.
Yeah. So this will satisfy my BCNF condition, right? Now D determine EF. For the relation R, A is the key,
it's
right?
Not a, yeah, A is a key, so it's not satisfying.
Yeah.
So you decompose that further.
Yeah. Now for here, BH determines CG is a key here, right?
Correct.
So these two function dependencies not satisfying my BCNF condition. I can simply decompose it into AD, DEF, BHCG, and GH, and at the last ABG. So all the relations are in BCNF here. You can see it is R1, R2, R3, R4, R5.
Are we sorry? Are we directly looking at BCNF or 3?
Oh, sorry. Yeah, we're checking for 3NF only, right?
Okay.
Sorry. For the 3NF, there should be no partial dependency, right? This non-prime attribute determining non-prime attribute. For BCNF, it is the condition that left-hand side must be a super key, right?
Correct.
Yeah. So here you can see. Okay, so in this, both the F1 and F2, is there any transitive dependencies there? In F1 or F2, any transitive dependencies there?
In F1, sir.
Sorry?
F1, A determines D and D determines EF.
Yeah, so A determines D is a transitive dependency. Yeah, so D determines EF is a transitive dependency, right? Where A is a key for this relation R1. So this relation is not in 3NF, right? Yeah. So this relation is not in 3NF because it is transitive dependency. Now, let us check for F2. BH determines CG, and for this also it is not in satisfying 3NF condition. Now, if I take the closure of this thing, I will get, like, I need to decompose relation R1, right? So I can take the closure of D, right? So if I take the closure of D here, what I will get? DEF, right? So I can decompose this R1 as R11, and what will be my R12 here? Like AD, right? Hello?
Sir.
Yeah. So now let us check for F2. So this is not satisfying my 3NF condition. Just take the closure of G. If I take the closure of G plus, what I will get? GH only, right? So I can make this as R21. So my R2.
H is a prime attribute, no, sir. See here, BH, since BH is the key, H will be a prime attribute and it satisfies 3NF, no?
H is a prime attribute, right? And G is not a prime attribute.
G is also prime attribute.
No. For this relation R2, BH is the key, right?
Right.
Sir.
Yeah. So G determine H. Okay. So this is the check condition we have to check. Like for it is a non-prime attribute, right? And this is a prime attribute. Is there a transitive dependency here?
No.
No. Right. And G is not a key, right?
Yeah. So it meets the second condition for 3NF.
Sorry.
So it meets the second condition, right? The right hand side is actually part of a prime attribute. Is a prime attribute. So we don't have to decompose this.
Yeah, we don't have to decompose this. So this is in 3NF, but not in BCNF, right? We'll discuss. Yeah, we'll discuss such corner cases for 2NF also. Like, what is if there is a combination of prime attribute and non-prime attribute? Okay. So maybe Nirav sir will take that part. But I'm just going through this one question. Now we need to decompose this relation into BCNF, right? So I already decomposed this relation R1 into R12 and R11, right? So DEF and AD. This relation R2 is in BCNF, it is in 3NF, but not in BCNF, right? So we need to decompose it, right? Because this condition is not satisfying a BCNF condition. For BCNF condition, left hand side must be a key, right? Are you getting it? Hello?
Yes, sir. Yes, sir.
So let us decompose this R2 as just simply take the closure of this left hand side, that is G, and I will get GH. So it will be GH, and R22 will be, what will be my R22?
BH?
BCG.
BCG.
Yes. Like, okay, so what are the remaining attribute here? BC, right?
BC, yeah.
Now, in order to make this R R21 and R23 as a lossless decomposition, which attribute I have to add here? either G or H. If I add H here, will I get R21 or R22? If I add H here, so intersection will
No,
be
sir.
H, right? So I will not get R21 and R22, right? So what if I add G here?
We get GHR21.
Yeah, so we get GHR21. So this will be my R1. So this will, okay. So this will be my R11. This will be my R12, R21, and R22, right? And my fifth relation will be this RBG, sorry, ABG. That is ABG. So now all the 5 relations are in BCNF, right? So which is the correct option here? DEF, AD, GH, BCG. As you remember, like initially we have considered this as the key, right? ABG. If I considered ABH, then this will be a correct option, right?
Yes.
Yeah, initially you have considered ABG as a key here, right?
Yeah.
I can consider ABH also, right? If I consider ABH, then this will be a correct option, right? Hello?
Yes, sir. Correct.
Yeah. Okay. So any doubt in this part?
Just this R2, I'm a little confused about the decomposition.
Yeah.
We have
So,
BHCG as this one, and we have 2 dependencies. BH maps CG and G to H. BHCG is a super key. BH is a super key.
yeah.
And GH, G is a, both G and H are prime attributes, right? Technically, or are we just looking at it within the context of
G and
R2
H,
alone?
you can see.
Sorry.
Yeah, G and H is a prime attribute. Now, for this relation R, only BH is the key, right?
BH is the key. So GH is not really prime attributes.
And for this relation R2, only B and H will be prime attribute, right?
Right. So we are looking at only within the context of R2. So
We are checking for R2 only, right?
Correct. Okay. So therefore, G and H becomes transitive dependencies, right? The meaning non-prime to non-prime.
It is not a non-prime attribute, this one, right? H.
H is okay. H is.
So there are a few corner cases, like what if there is a combination of non-prime attribute plus prime attribute determining prime attribute, right? So that we'll discuss now. Like any doubt in this question, like you know how I decompose this and how we get this option, right? You can take any of this. There are multiple decomposition possible. If I take APH, I will get this option as the correct one, right? Okay. I think Nirav sir joined. Yeah, so
Yes,
Nirav
yes,
sir will
please.
quickly go through we'll summarize the week 6 concept, like normalization part, and he will also discuss few corner cases also, right?
Yes, sir. Yes.
Okay, yes, sir.
Okay, so what I guess is, I think you all are now aware about the rules of normalizations, right? I would like to ask the participants if they have any doubt regarding the rules of normalization.
I mean, the rules themselves are clear. I don't know if it is the right context. I'm just trying to still understand the 3NF and BCNF dependency. No, I mean, the condition where it allows for, non-prime or a prime attribute to be on the right-hand side. The third condition for 3NF.
Yeah.
Versus the stricter BCNF. I'm just trying to understand what it achieves from.
Okay. So what I can do now is, I think, let me summarize the entire thing of normalizations and all the rules of different types of normal forms, right? Slightly in a different way so that you all can easily understand and can solve certain examples as well, right?
Sure, sir.
So yes, so far I think the team has covered all the rules with the keys, non-keys, prime attribute, non-prime. You are aware about this, right?
Yes, sir.
Now, the thing is, Suppose we have any relation R, let's say some set of attributes available to us, right? So once you know how to find out the key attribute, definitely this relation will now comprises of two. One is key attributes, and second is the set of non-key attributes. Okay, and from the concept of key and non-key attributes, we have also identified another two aspects. That is, the attributes are prime attributes, and the attributes are non-prime attributes. Right. Now, as far as first normal form is concerned, it has nothing to deal with the dependencies or key attributes. Whether it is moreover related to the domain part. Domain means a set of all the values for any particular entity. So, for example, the domain for A is might be only numbers. Right? So, whereas you can say only digits are allowed or a combination of numbers are allowed. B might be it is a set of characters, right? In that way. So, domain can be of two types. One is domain can be atomic or domain can be non-atomic. So, whereas a first normal form claims that the domain must be atomic. In other words, all the atomic domain says that there are no multivalued attributes and there are no composite attributes. Something I'm not able to write it properly. Okay. So I hope all of you are clear with this rule of first normal form, right? Where we follow that the domain must be atomic. There should be no multivalued attribute. There should be no composite attribute. There should be no nested relation. That is like table within table or relation within relation, right? Now, from second NF onwards, we will focus on functional dependencies which are exist and key attributes, right? So I think you know that how to find out the dependencies from a given set of attributes in the table, right? The values are given to us. We will look at the every dependency will be like if I want to say that A gives B is present here, then definitely what I look is either A is unique or let's say for two or more than two similar values of A, there should be similar values in the B, right? That's how we define the functional dependency. I think you know how to find out it, right? So considering the case that you know how to find out dependency, how to find out key attributes, and then convert it into prime and non-prime, let us move ahead, right? Do you have any doubts in that key, non-key, prime, non-prime dependencies, how to find out dependencies or anything related to that? Hello?
Clear.
It is clear, right? Okay, so now the thing is, what do you think for any table? What can be a dependency type, a category of a dependency? As we know that all the attributes of any table is now divided into, let's say, prime attribute and non-prime attribute, right? Then definitely any dependency for any given relation R can be, just give me a 1 minute. I think I need to change my writing pad. Not working.
Hello.
Yeah, hello. Just wait a minute. Is the screen visible?
Yes.
Hello. Okay.
Yes.
Okay. Yes, I was talking about. Yes. Okay. So I was talking about if we have any relation with some set of attributes here, right? Down here. Then yes, the dependency can be of any of the categories, like where we can say either our non-prime attributes are depends on prime. Let's say our non-prime attribute depends on another non-prime attribute. Let's say prime attribute is depends on non-prime. Let's say prime depends on prime. So what do you think? Once we categorize our every attributes of a table or a relation, right, into prime and non-prime based on key attributes available with us, right? Can we have any dependency of any of these four categories? Let's say every dependency will be of any one of these categories. Is it so?
Yes.
Right? Because now see, all the attributes of a given relations are now divided into prime attributes, set of prime attributes, and set of non-prime attributes. So obviously, among them, once the dependencies are exist, it will be one of this, right? Or combination. So as far as second NF is concerned, it will deal with this first kind of category of dependence, where non-prime attribute is depends on prime. So what is there in the rule? That if any non-prime attribute is depends on prime, it must be fully functionally dependent, right? It must be fully functionally dependent. That means now second normal form have a concept of two things. One is partial dependency, and second is fully functionally dependent. And this concept of partial and fully functional dependency is applicable only for this first category, right? For rest of the categories, like where non-prime depends on non-prime, prime depends on non-prime, prime depends on prime, we never look for such kind of partial dependency or fully functional dependency. So if any non-prime attributes, if we consider the first case, if any non-prime attribute, it depends on prime, it must be fully dependent. What is the meaning of it? The meaning is it must be depends on key. So when I say a non-prime attribute is depends on prime, and this prime is nothing but the full key, right? Then it is called fully functional dependence. And then what is partial dependency? Partial dependency is one where if non-prime attribute is depends on prime, and this prime is just a part of key. Are you all clear with this?
So essentially, the meaning of this is just trying to. So essentially, the meaning is that because if an on-prime is partially dependent on
Prime.
key, it means that it
Right.
is probably creating a subset of a relationship, and therefore there is
Yeah.
redundancy.
Yes. Exactly. Right. So that is the concept. So we are looking for the things like where if non-prime attribute depends on prime, it must be fully depends on key. Right. So rest of the cases, I mean, rest of the three conditions are allowed for the second normal form. Right. So again, if you want to say what is allowed and what is not allowed for second normal form, right, we can categorize this way. What is allowed for second NF and what is not allowed. What is not allowed here in our case is we have a set of dependencies. We'll look at each and every dependency one by one. And when we check that whether every dependencies satisfy the rule of allowed, right? Or any of the dependency, if you find that if non-prime depends on prime, which is partial, right? Then it is not. Any of the single dependency from a relations, if there is a partial dependency exists, right? Then it is not allowed and the entire relation is not in second NF. Then what is allowed is rest of the three conditions are allowed. So let's say for second NF, it is like if any non-prime is depends on non-prime, yeah, it is fine, it is allowed. Let's say if any prime depends on non-prime, it is allowed. Whether it's any prime depends on prime attributes, it is allowed. And any non-prime which is fully depends on prime, right? Which is fully depends on prime, that is allowed, right? So I hope with this the rules are clear now. For second NF, what is allowed and what is not allowed, in order to check whether the given relation is in second NF or not. Is this thing clear?
Yes, sir.
Right.
And,
Okay.
and just to confirm,
Right.
it doesn't mean that the allowed ones don't create redundancy, right? The allowed ones will also create redundancy.
Yeah.
In second enough, we will only allow this.
In second NF, we will allow this. Now, allowed dependency will create redundancy. Then we'll solve through the consecutive dependency, like third normal form or BCNF and so on.
Okay.
So far, second NF is concerned, what is allowed and what is not allowed. Let us check whether the given relation is in second NF, satisfy the condition of this or not, right? So our expectation is what? The relation is given to us, and let's say four or five dependencies are given to us. Each and every dependency satisfy the rule of allowed conditions for second NF, then and then the entire relation is in second NF. Otherwise, we need to convert that. I think that is something which is already been covered right now. How to decompose the relation, how to check whether it is lossless join or not, right? And when you decompose, we have to make sure that every subtables we have decomposed, right, must satisfy this allowed condition of second. So now every table will have this kind of dependency. Every relation contains these categories of dependency, and hence it is in the second F. Means each and every individual decomposed table or relations are now in second F, right? So what is the thing that we need to take care about when we convert into the normalization is we are allowed to change the key attributes. Because we decompose the tables, obviously key attributes will be changed, but we are not allowed to change the dependency. Dependency is something which we must have to preserve, right? So whether we decompose our entire table into 2 tables or 3 tables or let's say 4 tables, it's fine. But make sure that the initial set of functional dependencies is given to us, right? It must satisfy through this decomposition, right? And that's why I think the team has already covered how to check whether the dependency is preserved or not, and how to check whether the decomposition is not, right? Okay.
Yes, sir.
So now moving ahead, this is for, that is the first condition is for second NF. But if we go for this second category, right, where non-prime depends on non-prime, which is allowed in second NF. So 3NF is strict than the second NF. It demands that the relation must be first in second NF. Apart from that, if any non-prime depends on non-prime, it is not allowed, right? So for third NF, we have to now look at this condition where non-prime depends on non-prime is exist. Okay, then it is not in the third. So in another way, we can say another 2 categories which we have categorized here, it is allowed. And how do we define this? Rest of the 2 conditions, that is prime depends on non-prime, prime depends on prime. So for that, again, we will have this where we will categorize what is allowed and what is not allowed for third NF, right? So let's say what is allowed and what is not allowed. So what is not allowed is, as per the rule is, transitive dependency is not allowed. So when we say transitive dependency, there are two types of dependency. Transitive dependency, which is created due to non-prime, or which might be created due to, right? So let us consider both of the case. Suppose you have a dependency something like this. A non-prime depends on non-prime, and the same non-prime is depends on prime, right? That is the first case. The second case is, let's say a non-prime is depends on prime. That prime is depends on prime. So what we are talking about is in third NF, what is not allowed is transitive dependency due to non-prime is not allowed. This is the category where transitive dependency is created due to non-prime. Which non-prime? This middle non-prime, right? So when we say transitive dependency due to non-prime, it eventually will have non-prime depends on non-prime. And hence, the conclusion is if you have any non-prime attribute depends on non-prime, another non-prime attribute, right? And that's why we are focusing on the second condition or third NF, right? Non-prime depends on non-prime. So when you have a non-prime depends on non-prime, it will have internally transitive dependency which is created with that non-prime, which is something which is not allowed, right? And if it is not allowed, then also we also have to what is allowed. So again, we have a relation with all the set of dependency, and let us check that whether our each and every dependency satisfy this condition, which is I think okay. Let me write it out in the way you have understood it. You understood it with X gives A rules. Right? So let me write down that X gives A, where let's say X is a key or this A is prime. Any one of this condition is true for a given dependency. Yes, it is in the third NF. So what third NF demands is our every dependency will have this form where either LHS is a key or RHS is prime attribute, right? So if when RHS is prime attribute, we don't care about what is there in LHS. And hence, you can again look at these two conditions, right? If RHS is prime, I'm talking about this, then LHS might be non-prime, doesn't matter, right? So either this RHS is a prime or this LHS is a key, then it is the third NF. So if you find that any of the dependency has the form like non-prime depends on non-prime, then of course we need to again decompose the table into subtables or decompose the relation into subrelation in such a way that dependency is also preserved and every dependency satisfies this condition. Every dependency is LHS is either a key or RHS is either a prime key. Is this thing clear?
And again, this second condition is allowed where no, a non-prime depends on a prime is allowed because in any case the prime is part of a key and it is determining all the other attributes, and therefore the redundancies and
yeah, therefore the redundancy. And see, the second case is when we say we are looking at this, right? Third NF confirms that the relation must be first. Sorry for this. I think I already changed my writing pad, but still there is some issue. For third NF, the relation must be in the second NF. Now, if you say relation is in the second NF, now go for this condition. If I claim that in my relation, there are some dependencies where non-prime depends on prime, obviously there must be fully functionally dependent because it satisfies the rule of second NF. As I'm checking for third NF, I confirm that it is already in the second NF. Hence, this non-prime depends on prime is fully, right? And then this prime depends on prime. So that's fine. Such kind of transitive dependencies allowed for third NF, right? The only thing is the transitive dependency due to non-prime is. So I hope it is clear what is allowed and not allowed for third NF. See, this will give you an idea about how to quickly check whether the given relations with a given set of functional dependencies are in the second NF or third NF, or let's say BCNF, right? So you can just go through this allowed and not allowed conditions, and you can quickly conclude what it is about. I hope it is clear. Anyone
Yes, sir.
having any doubt? Okay. So then BCNF is very simple, right? One thing to check about. It is even more strict, right? So when I say in third NF, I told you that one of the condition is like, suppose for example, right hand side is prime, then we don't care about what is there on LHS. Even if it is a non-prime, it is allowed. Okay, this condition is allowed in third NF, but in BCNF, it is not. So what is there in the BCNF? BCNF says that your LHS must be, so for X gives A, it must be, right? So now we don't care about what is there on the RHS, but LHS must be. Now, ideally, it is very difficult. When we say, even if I decompose my table into subtables, or let's say I decompose my relation into sub-relations, right? Let's say R is now divided into R1, R2, R3, and so on, right? It is not every time possible that whatever initial dependencies are given to us, LHS must be a key. Even after the decomposition, some dependency not satisfied. So BCNF is the only form where we can say that even if, let's say, some dependency does not preserve, it's fine, it is allowed. But up to third NF, all the dependency must be preserved. Now, when we go for even more strict version like BCNF, then obviously we have to compromise something. Like one or two dependency, in my case, let's say it is not satisfying, right? It's fine. But still, once I decompose R into R1, R2, and R3, now it is in the. So sometimes, not every time, but sometimes this is the case that in BCNF, dependency might preserve, might not preserve. Then in that case, you can convert your database, right? So I hope it is clear.
Sir, in BCNF, even the prime determining prime is also not allowed. Correct, sir? Am I right?
No, it is allowed. Prime determinant is prime allowed considering the case that this prime is now key.
Okay.
This prime is nothing but a, is it so? Right? Now see the
Yes,
case.
sir. Yes.
Sometimes now our key is also of two types, right? A key might be a simple key or it might be a composite, right? In case of a simple key, let's say A is my key, then obviously A is a prime attribute. If I say A derives something, it's fine, it is in the BCNF, right? But if it is composite attribute, let's say AB, right? Then A derives something, we need to look into this. What we want is LHS must be. In that case, what we need is AB gives something, right? That
Okay,
way.
sir.
So this is the summary of, I think, all the rules, right? You can apply and you can check whether what is allowed and not allowed. So with these four categories of conditions, right, starting from first, and now then after, once you say that non-prime is fully depends on prime, okay, it is in second NF. Now this must be satisfied. Apart from that, additional restriction is non-prime depends on non-prime is not allowed for third NF. Okay, additional restriction is if any prime it depends on non-prime, it is not allowed in BCNF, right? So step by step, the restriction in terms of a dependency formation is there, and in that way, you can always check whether it is in which normal form our given relation is, right? So considering these four category in our mind, and first case is define a key attribute. Let us have a set of prime and non-prime, and then just check these four conditions, and then you will be clear whether it is in the second NF, third NF, BCNF, what is allowed and what is not allowed, right?
And just a question. So once we decompose, say if one relation we take R and we decompose into R1 and R2, let's say.
Okay, fine.
And then now we are again decomposing, let's say R2 into something else.
Okay.
Now we repeat the same process for each relation separately. Is that like we have to find out the prime and non-prime of that particular relationship? R2
Yeah, that
and
for
then
that particular relation, right? Because now once you decompose, you are talking about that subpart or subtables, right?
Right.
So for every such subtables or sub relations, you need to check this condition. Because now what we want is initially it was R, but after decompose it is now R1, R2, R3, and R4. So all these R1, R2, R3, and R4 must satisfy the condition of, let's say, either second NF or third NF. Then only we can say these all four are in this particular normal form.
And plus they will have their own prime attributes and non-prime attributes now.
Yeah. They will have their own prime and non-prime attributes.
Okay.
So that's why the key attributes will be changed. Initially, R is having, let's say, AB as a key attribute. Once you decompose them, their key attributes will be changed. So key attributes for R1, R2, R3, and R4 will be changed once you decompose. What is not changed on where we need to take care about is the dependency must be preserved. We cannot change the dependency, right? So initially, let's say A derives B. Then till the end of the BCNF, once you convert it, it must be A derives B. It should not be like now B derives A. Reverse is that. I have changed my dependency just to satisfy the rules. We are not allowed to change the dependency, right? Dependency must be preserved. It is initially there.
So when we go from 3NF to BCNF, it is possible that some dependency might have to be, some dependency is not preserved, right? So how do we decide which one to drop?
So that depends on your real-time application. Now, generally what happens, sir, the dependencies are nothing but these are nothing but the requirements, right? So if some of the requirements in your system, in your computerized system, if you want to compromise, it's fine. You can convert up to this. But if you stick to your initial dependencies, right, it should be there in my system, real-time system, right? Then don't go for BCNF. Up to third NF, it can be normalized, and then after it can be implemented. So sometimes redundancies are there, right? And we keep redundancy. We try to reduce redundancy as much as possible. It's not like we remove entirely at any cost. If dependencies are compromised, okay, we have to stop, even if the redundancies are there. But in that case, once you convert up to third NF, there will be no redundancy, or it will be reduced as much as possible.
So in the algorithm that sir had presented in the slides in his classes, right, to calculate the 3NF, I think the algorithm he mentioned was to first find the canonical cover of the dependencies and then use each dependency and then decompose based on that. That's the method I think he had put in. So does that mean that we use the same canonical cover set or converting it to BCNF also, because then the same thing is can be used, right?
Yes, sir, definitely. Same canonical cover, you can use it for BCNF.
Okay, and then amongst that, if there is anything that we have to drop because of meeting BCNF, then we'll have to just choose based on what is.
We have to choose based on that, right? Now, if let's say it is about questions and answer, and we have to convert into BCNF, it's fine. You may compromise some of the dependence, but anyhow, you have converted into BCNF. But if it is the real world implementation of any real world applications, right? Then you have to choose what you want to do, right? Because see, we are discussing normalization, but at the same time, denormalization is also there. And denormalization is the reverse process of normalization. So sometimes in some of the system, it is also possible that denormalized database is needed in order to get an efficient result, right? So let's say I have 1,000 attributes and more than thousands of rows, but I want only one particular attribute and one particular value. Of course, the normalizations plays major role here. Right? If I have already decomposed them, obviously the access is very faster. Even the efficient storage is there. But almost all the time in my real world applications, I want all these attributes and all these tuples to be displayed in different way. Then I don't need to normalize them. Because normalization is once you decompose, now the complexity is join. Join is the biggest complexity here. Suppose you have decomposed your initial relation into 10 sub-relations, and now most of the time your task is to join out of 10, 6 or more than 6 relations, join them and give the answer or display the answer or display the analysis, right? Then that join is very complex. It's a time-consuming process, right? It depends on application, it depends on your task, depends on your what you want to do with your database, right? In that way, we have to choose the particular normalization in the real world applications. So yes, denormalization is equally important, right? So that depends on how you have stored your data. If you want majority of them, don't normalize them. Even if the redundancies are there, it will give you the efficient result in the faster access, right? Because join is a bit complex and it is again a time consuming in that way. So I hope it is clear.
Yes, sir.
Yes, Piyush, anything else do we need to cover? Okay. One more thing is, suppose now when we are talking about second normal form, where we want fully functional dependency, right? We are just assuming that LHS is a prime or LHS is a non-prime because of these categories. Now, what if there is a combination of prime and non-prime? So I'm writing here, I have a two attributes. One is prime, another one is non-prime. It's a combination of prime and non-prime, which derives non-prime. Now, in such case, how to apply these rules of allowed and not allowed? What do you consider in such case? Let's say I have a combination on LHS, the combination of prime and non-prime attributes. And on RHS, I have a non-prime. Should I take one example?
Sure, sir.
Okay, I think let us go through one example. Okay, so on your screen, can you see that the relation R with A, B, C, D attributes?
Yes, sir.
Right, and we have initial set of functional dependency. Can you quickly tell me what can be the key attribute here?
AB.
AB. Okay, and when we are talking about key attributes in normalization, see, we use the word key attribute. That means we stick to candidate key, right? And candidate key can be always more than one. It is possible that it is more than one, right? Whereas primary key is always one in any table. So when we are talking about key attribute, we are talking about candidate key. And all the rules which we have discussed so far, it is related to candidate keys. So if more than one keys are present, all those must satisfy the rules of that allowed and not allowed, right? Okay. So do we have only one key attribute here, which is AB, someone says?
AC also.
AC also. Considering the case that AB and AC are the key. Any other? Okay. If AB and AC are the key attributes for this relation, right? So of course, the prime attributes are A, B, and C. Right? So there are total 3 prime attributes. There are 2 key attributes, A, B, and AC, but there are 3 prime attributes. One is A, second is B, the third one is C. Now we have already gone through the rules of second NF, right? In order to find out whether it is in the second NF or not, right? Obviously, we have to see that in RHS, if any non-prime attribute is there, which is depends on prime, and it must be simply dependent. If you go dependency wise, in this first dependency, Does it satisfy the rule of second NF?
It does.
Yes, because the non-prime C is fully depends on key, because AB is a key we have already identified. So this is fully functionally dependent, and as per rule, it satisfies the rule of second NF. What about this? Which category of this dependencies?
Prime attribute determining prime attribute.
Okay. So does it allow for second NF?
Yes, sir.
Okay. We don't have any issue as far as second NF is concerned, and we are discussing about second NF right now. So these two dependencies satisfy the rule of second NF. What about this third one? What kind of formation it is?
Prime attribute determining non-prime.
Is BC a non-prime?
No, sir. BC is a prime.
BC
D is a
prime?
non-prime.
So non-prime depends on prime. Is it so?
B and C are individually
Yeah, they are individually
prime attributes.
Prime attributes, right? They are individually a prime attribute. Okay. Now what to do in such case? Now obviously BC is not a key, right? But again, B and C both are prime. So this is one of the case, right? Where we have to look for or how to decide like whether it is, I mean, third dependency BC gives D satisfy the rule of second NF or not, or whether it is a partial dependency, whether what to consider it, right?
I'll treat it as partial because B and C are individually.
Okay. So in such case, what we have to do is we
It's
already know the rule. Sorry.
It is partial now because BC determines D and C again it is determining B also. No?
Yeah, exactly. So that is where I want to focus on. Right? We know the rule of partial dependency. Partial dependency says that if any part of determines the non-prime, it is partial. If any part of key determines the non-prime, then it is partial. So we have BC gives D. So the meaning of that is BC derives D. When you do BC plus, D will be the part of result. But what if not BC plus, if I do B plus? What if I do C plus? Are you getting? What I'm now trying to do is, I'm trying to check whether D is present when I do B plus, D is present when I do C plus, right? Why I want to check is because I know that B is part of B. I know that C is part of, right? So I want to just check that the D can be derived from just part of key or not, right? And for that, we can apply those rules of Armstrong's axioms, which you already studied. So when I do, let's say C plus, what will be the result of C plus then?
BCD.
Yeah. So D is present. D is present or not? In a result of C plus?
It is.
Yes, it is there, right? So that means, although it is BC gives D is given here, but from those axioms which you have studied, you conclude that only C, from this example, only C can also derive D. And whenever we say C derives D, is it partial or it is fully dependent?
Partial.
Yeah. Now we have proved that this non-prime is partially depends on this prime, that is part of D, right? And hence, this BC gives D is what? A partial dependency, and it is in the first normal form. When it is not in the second normal form. It doesn't satisfy the rule of second NF. We need to decompose this table into subtable in order to satisfy the rule. I hope I'm clear.
Sir, if there was no C determines B, then
Yes, then there is no partial dependency. Let's say B is also not. Let me take this example. Okay, let me take one more example where I think. Okay, now considering this, relation R with A, B, C, D, E attributes. Again, quickly, can you tell me what is or what are the key attributes here?
Sir, sorry to interrupt. The definition of partial dependency is that a subset of the candidate key should not determine a non-prime attribute, right?
Yeah, exactly.
So in the previous case, BC is anyway not, it's actually a subset of the, even if you take B and C individually, they are subsets of candidate key, and therefore by definition, they'll have to be partial dependent.
Yeah, they have to be partial dependent, right?
Irrespective of whether C determines B or not.
Okay, irrespective of whether C, but in that case, C will always determine D.
C will always determine D. Yeah. So in that case, it will be partial dependency.
Yeah, it is. Yeah, thanks.
Okay.
So in either of the way, it is partial dependency, right? That is fine.
Okay, sir. Okay.
Okay. Now this is slightly different case, right? What can be the key attribute here?
AB.
AB. And is AB is the only key, or do we have any other key attribute?
Looks like AB only.
AB is the only key attribute, right? So that means when we say AB is the key attribute, prime attribute is A and B. And again, this FD1, does it satisfy the rule of second NF?
Yes, sir.
Okay. Because non-prime is fully depends on key. Now what about this? BC gives D. Now we see that D is something which is non-prime. But this LHS is a combination of prime plus non-prime. And we cannot decompose them into two dependencies like B gives D or C gives D. Right? So now it is BC gives D. Combination of BC is giving you the D, right? Whereas one is prime, one is a non-prime. So whether it is considered to be as a partial dependency or
intuitively it is partial, right? Because it's not the full key, like it's not ABC determining D or anything like that. So only one portion of the prime attribute and some portion of a non-prime attribute is determining another non-prime. So there could be redundancies because of that. I'm just thinking aloud intuitively.
Okay. So it says that combination of BC derives the D. So when I do BC plus, obviously D will be the part of result. In order to check whether D can also be derived from just part of key or not, because our partial dependency definition is something like this. If any non-prime depends on prime or part of key, this prime is part of key. So if we stick to this rule, obviously BC is not any part of key, but then to check whether this non-prime, that is D, which we are looking for, can be derived from part of key. So we have two options, B and C, out of which C is obviously not a part of key, but B is there. When we do B plus, and if we get D into the result, then obviously we can claim that B gives D exist here, right? B gives D exist here if B plus derives, right? And if we prove that B plus derives D here in our case, and B gives D is there, then obviously now it is non-prime depends on part of, right?
Right.
So let us check now. Is it possible?
No.
Let us do B plus.
B plus doesn't give D.
So that means, what is the meaning of that? When you say B plus doesn't give D, the meaning is B alone does not derive D. And hence, the partial dependency does not exist. Partial
Okay.
dependency is not exist. So even if it is BC gives D, for third dependency, I think there is no any doubt. CD gives C non-prime to non-prime. So it is allowed for second NF. But as far as second dependency is concerned, BC gives D. Right? Partial dependency is not exist here. Hence, it is in the second NF because all three dependencies satisfy. Now see the cases, right? I hope you are getting this. So in previous case, what we have done is we have considered two different prime attributes. Two different prime attribute means they are the part of different keys. And then we have concluded what is there. And here, one is prime and one is non-prime. So yes, such kind of combinations might be there in the LHS. But in that case, what we have to do is we have to apply the rules of whatever you have studied, like closure set of FDs and axioms. So let us try to apply all those rules here and try to check whether actually indirectly partial dependencies exist or not. I mean, D or any such kind of non-prime attribute like D is partially depends on key is exist here from a given set of dependencies or not. In that way, we can check. I hope it is clear.
Yes, sir.
Yes, sir.
These are these are few of the cases where we can say we need to just focus on when we apply those rules of what is allowed and what is not allowed, right?
So we'll have to take a closure from that particular
Yes,
prime
definitely.
attribute and find out if we are able to determine the right hand
Yeah,
side. If
right.
so, then it's a partial, otherwise not.
Right, exactly.
Okay. Thank you.
Right. Because at the end, meaning of partial dependency is this only. No? LHS prime, if you do the closure of it, right? And if non-prime is derived, that means that dependency is inherently present here. Right? It is not mentioned in the given set of F, but it is there.
Yeah.
Piyush, anything else?
No, yeah. So I think we have discussed the normalization part. Any doubt in this part, normalization? Or any doubt in 4NF, like multi-order dependency? Anyone?
Yes, sir.
Yes.
Sir, while decomposing to 4NF, do we need to consider both of them as super keys? I mean, in the lecture, he has taken man, phone together as a key, or
No.
is it just man as a key?
Okay. So for 4NF, our relation must be in BCNF, right? So it should satisfy all the BCNF condition till BCNF, right? And there should be no multi-order dependency in that. So in slide, sir has explained one example, right? So that's what you are asking.
Yes, sir.
Let me see.
And in one of the practice assignment, they have asked like convert it into 4NF and P is a super key.
Okay, let me check.
So why can't both PQ be a super key?
Let me check. Practice and question number, can you tell?
Just a minute, sir.
Question number 4. I'm presenting this one. question number 9 is based on MVD. Question number 6 is also not 6.
Activity 6.4, sir.
Okay, activity.
Sorry.
Question number.
Question. Last one.
Last one. Okay, this one. Okay, this one. Is it visible? Hello.
Yes.
Okay. Activity 6.4 question 10. Okay. So here you have to consider one relation and only one functional dependent. Okay. This multi-order dependency. Only one functional dependency. And one multi-order dependency. If we decompose Z into Z1 and Z2, then which of the following is true? Yes, Madhu. Can you tell me how did you approach this question? This is a functional dependency. Okay, arrow is showing double-headed, but consider a functional dependency. We determine Q.
Yes, sir.
Yeah.
So we'll first find the.
Yeah. See, so we have to check here whether Z1 is in 4NF or not, right?
Yes, sir.
Yeah. So Z1 has only two attributes, that is P and Q. So for by definition of multi-order dependency, there must be at least three attributes, right? See, if
Yes,
there
sir.
are A, B, C, if A is multi-determining B, and where B and C are two independent attributes, right? There must be at least three attributes such that their B and C are independent attributes. Then I can say A multi-determine B or A multi-determine C. Okay. But first it should satisfy those four conditions, right?
Okay.
Yeah. So for Z1, there are only two attributes, right? So we can say that Z1 is in 4NF. Right? Because
yes, sir.
it should require at least three attributes. If there are no three attributes, then we don't no need to check any for any condition, right? So Z1 is
Yes,
in 4NF. Now P is a key for Z1 or not. So what are the applicable functional dependencies to Z1? Only one is there, right? That is P determining
P
Q.
determines one. Yeah.
Yeah. So here P is the key, right? For Z1.
Yes, sir.
Yeah. So this option is correct. Z2 is not in 4NF. Now let us see for Z2. For Z2, we have Q, R, S, T. But here just multi-order dependency is there, right? Q determine ST. Right here you can see. So this is not in 4NF. This is condition is true. And Q is the super key for Z2. And for Z2, is any functional dependency applicable here? For Z2, we have only one functional dependency, right? Can we say Q is a super key for Z2 here?
No, sir. It doesn't contain R, right?
What are the functional dependencies for Z2? No.
Q
Right?
multi-determining ST.
No, that is an MVD, right? I'm talking about functional dependency, FD.
Oh.
Nothing else.
Nothing, right? So Q is a super. In that case, what is the key here? The combination of all attributes, right?
Okay.
Yeah. So this is not correct. So Z1 is in 4NF, Z2 is in not in 4NF. So this one is correct. Yeah. So I think A and C are the correct option here, right?
So there's some rule that I mean maybe confusing. If Q multi-determines ST, then Q also multi-determines R, right? No, is it not like it
Q
says R minus something like that?
ST, then it should determine Q R minus ST. So that will be Q multi-determine R. Sorry, here R is our Z2, okay? which is a relation R. So Q will also multi-determine R also, right? There are few complementation, not complement, there's few rules for that ability. So say if I say alpha multi-determines beta for a relation R, then I can say alpha multi-determines R minus beta. Yeah.
And because it now by derivation, if Q multi-determines R also, would you say R is a super key?
No. Sorry, Q multi-determines R, right?
Correct.
I'm writing it here. Q multi-determine ST and Q multi-determine R also. So Q is the super key, that's what you are asking, right?
Yeah.
No, because we calculate this key based on the functional dependencies only, right? Not a multi-value dependency.
Correct.
Yeah. Q is not a super key here.
Right.
Sorry, what happened? Okay. Okay, any doubt in MVD part? Okay, say suppose I have A, B, C. This one is A1, A1, B1, B2, C1, C2. Now, if you observe the condition and whatever the sir has explained in the lecture, if we take the combination of A1 with B2 and A1 with B1, like if I keep the, sorry, for checking alpha multi-determining beta, if I keep the alpha value same, and if I exchange the beta value and remaining, keeping the rest of the attributes same, and if you are getting the same tuple in the relation R, then we can say there is a multi-value dependency, right? So if I interchange this B1 and B2, keeping the alpha value same, what I will get? Alpha, sorry, A1, B2, C1, right? And A1, B1, C2, right? I'm just exchanging this B1, B2 here. So I will get these two new tuples, right? Here.
Yes, sir.
Yeah. So what is this condition? So there are four conditions for MVD, right?
T1 of alpha.
Yeah. So if so, let me just so if alpha 1 T1 equals to alpha 2 T2, then there exists few conditions. Now, what are those conditions? Alpha 1 equals to alpha 1 T1, sorry, alpha T2 equals to alpha T3 equals to alpha T4, right? Now, if I do the crossing here, exchange of beta value, I am getting A1, 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 A1 for four tuples, right? Now, what is this condition B2? I am getting two new tuples, right? What is this condition B2? Let us say this is T1, T2, T3, T4. You can check any condition, right? Like T3 beta must be equals to T1 beta, right? Sorry. T2 beta must be equals to T3 beta. And T1 beta must be equals to T4 beta, right? And then T1 R minus beta must be equals to T3, not T3. T3, no? T3 R minus beta, right? So T1, T2 can be interchanged because I am just considering this sequence, right? So if you see, we'll get the same for condition here, right? You can check for the sequence also, like for order T1, T2. So whenever you are going to check the MVD conditions, please make sure that while checking all the four conditions, you have to keep the sequence same, that is T1, T2, T3, T4. Now it is not like it for checking first condition, you will consider this as T1, T2, T3, and T4. And for checking second condition, you will consider this as T2, this one as T1. It will not like that. For keeping all the conditions, we have to keep the sequence, so not sequence like or order of a tuple same, like T1, T2, T3, T4. Or either you can consider T2, this one as T2, this one as T3, this one as T4, anything. But it should satisfy those 4 conditions, right? Any doubt in this part? I'm ready. Just practice few problems. There are few problems in practice assignment also. Okay, so I think the deadline for the week 6 is extended till tomorrow. So you can attempt the week 6 graded question also. We have covered all the concept from week 5 and week 6. Any doubt in both the weeks, like any conceptual doubt or any question you didn't understand from week 5 and week 6? Anyone?
Sir, one request I have is, hello? Hello?
Yes.
Yeah, just one request is the next session when it comes up, this normalization, if you can just walk through using a real life this thing. What is happening to me is that when we are always into this ABCD, PQST
Right.
and all, it get into basically to assimilate into the brain, and often distinguishing one between other, it makes a lot of issues actually. Okay, so if you can just work out on one a particular real life database, we can say, like in that stat2 we had that power play, IPL power play or something like that, or just an Excel sheet with some say 10-15 columns, and if we can just kind of decompose it and work it out, the normalization on one step, that things will make it very clear actually. Yeah.
Okay, yeah, sure.
Anwar, are you in the previous session?
Previous session, which one it is? Which one it was?
I think Saturday session.
No, Saturday, I think I must have been there. I must have been there on Saturday.
No. If you were there or not, it's the previous session. Previous Saturday session, 12 June. I think 12 June. 12 or 11 June, I think. So we discussed in the real life example. Can you watch the previous session? There was one example of the supply tables, how to relate from the first NF to the second NF and third NF and the BCNF also.
If I had missed any session, normally I go through the YouTube this thing. So, but I don't remember it exactly.
So Pradeep actually is asking for a real world case. Like if we have one table having say 10 attribute, and then we can decompose that into till like 3NF or BCNF. Right, Anwar?
Yeah. Yes, sir. That session is also in the similar kinds. The supply table is decomposed into 2 tables. Then in the further how to, from the one database further how to divide it. That is one simple. So it easy to understand also.
Yeah.
Otherwise, is thing got complicated, right? It takes a large example.
Yeah. So okay, Anwar, you can go to the last session also. I think we have discussed one, but we'll think about taking one like whole real world example. Okay.
Yeah. Normally, what happens is that the motivation comes through when we are actually kind of simplifying certain complex things,
Right.
and if we feel like okay, this was this simple, then that makes a lot of difference actually. Okay.
Yeah, okay. Like we are using this ABCD just to simplify our calculation, right? Like procedure. Because otherwise we have to always write that, okay, it's attribute and then comma attribute and determining this. So there is one question in practice. If you go through that, it will take a lot of time and it will be confusing. So what I will do, I will just consider this as A, B, C, and I will go through the right. I'm just will present one minute. So I'm talking about
that's okay then.
Yeah.
Yeah.
So this one, like it will be confusing, like while checking the condition. What I will do, I will just consider this as A, B, C, D, and just create the functional dependency based on that, and then I will check it, right? Yeah. Okay, but still, I will discuss with the team and see whether we can come up with one example or in a real case thing. Okay, real world study.
Or rather than a live session, you can just make it into a tutorial form or something, and 10-15 minutes video will be enough. But it has to be completely on a walkthrough model, actually.
So, like we have one tutorial on case study on ER diagram, like that, right?
Yeah.
Okay.
Yeah, actually, week 5 had a lot of tutorials. Week 6 doesn't have any tutorial. Actually, week 6 needs a couple of tutorials, I think. Of course, the live sessions are clarifying the doubts, but I think going forward, a couple of tutorials on week 6 will really be helpful.
Yeah, normally what happens when I get jammed by time, I normally watch only the tutorials and then attempt the graded assignments, because sometimes it happens so.
Yeah, week 5 had a lot of tutorials. They were all very useful, actually. Similarly, I think we might need some tutorials for week 6.
Because that week 5 is the prerequisite for week 6, right? Without understanding those concepts, we cannot go for week 6.
Yeah, what I'm saying is week 6 also needs tutorials. Yeah, some basic, as Mr. Anwar said, some basic examples taking us through right from the beginning to. I think Professor has also attempted one of the case study. He has done a slide, but I think it's a little more simpler than that. May be useful. He has done it on the university database, library database, I think, but something a little simpler will certainly help.
Okay, sure. Yeah, we'll discuss with the team.
Yeah.
Like what we have discussed initially, like take one example and decompose into BCNF or 4NF, like that, right? Like maybe real world example with having the attribute name instead of ABCD, right?
Correct.
Okay, sure. Yeah.
And just out of interest, is week 6, 5 and 6 the hardest part of this entire 12 weeks, or something else?
Conceptually, you can say that, yeah.
It's more abstract, right? This is the most abstract part.
Because this is the core of database, right? Database design.
Right.
Even if you go for any interview, they will ask questions from most of this week only, week 5 and week 6. This is more important.
It is moreover, rather than designing a database, it is moreover optimizing the database after the designing.
Right.
Because initial design, you might be prepared through relational model or like ER model.
ER diagram.
ER is basically a conceptual model, which will capture the concept of any real world application. But when it goes to implementation, before implementation, it needs to be optimized. So these normal forms are nothing but the way to optimize. Let us decompose and let us prepare a design in such a way that so that we can get efficient results, faster results, and there should be a reduced redundancy. So in terms of storage and in terms of accessing speed, it will be better. It is like optimizing the things through normalizations before we actually implement. Otherwise, initial design might be prepared through some ER model, let's say relational model.
It's all depends on the context also. Like optimization, when we say reducing redundancy might not be the optimization for certain scenarios.
Yeah, certain scenario it is not there. That's why I told you that denormalization is also important.
Yeah.
So again, it depends on context. It depends on real world application.
Okay. I think if there are any further questions, then we can close this session. Any doubt, any question, anything we can ask.
Yeah, what I felt was that because this 5 and 6 is the heart of this entire course, DBMS. So 5 and 6, let us have some more videos basically elaborating the concepts and all those things. Because what happens, I'll tell you, I'm a working professional, and the way what happens is like now, you people might be very comfortable basically like plotting the dependency, then A to B, B to C, C to D, like that if it goes. But from our side, what happens is that when it gets into 3-4 steps, basically it becomes very difficult for us. Okay. So then we have to again go back, then come back, because in real life the way we address all these things is it's different, and all the time we might not be going through all this theory and all, even though we are practicing all these things, right?
Yes, yes. Okay, we can plan some tutorial for week 6 also. Okay, any other thing? Okay, so in DBMS we have online proctored exam, which will cover week 2 and week 3 SQL query. So we have to plan one session for that, like for SQL practice session. Because we already released a 30 question, like for SQL thing. You can go to the PostgreSQL resources folder. So what we usually do, we discuss those questions only in the live session. So better
you have released what exactly? I did not.
SQL question for practice. Like we have released some 30 SQL question for practice.
It is there in the course menu?
Yeah, it is there in the portal. Yeah, you can go to the PostgreSQL resources folder. You can see questions are there, solutions are also there. So like I want you can go through the question, just try to solve it, and then come to the session. Like we can plan one session in the next week and one session in like before OP, that will be good.
The exam is on 26th, right? Or 25th? 25th and 26th.
25th to 26th of July, I think. Next month for DBMS. This month we are having for other courses.
For DBMS, it is in July, huh?
July, yeah.
Oh, I was thinking it is June.
There are only one OP for DBMS. Like few courses, there are two OP. So like for Java.
So it is only 2 and 3, huh? 2 and 3 weeks.
Week 2 and 3 and week 7 also, like Python database connectivity.
Okay.
Yeah, I will tell the pattern also, like how many questions will be there, and like there will be one question from week 7 also, like Python database connectivity. So I will tell you in that practice session, or I will send announcement also regarding that.
And for grading, it is a must to pass that exam.
Yeah, so it's a must pass exam. 25%, I think. Let me check. Yeah, 25% is required.
Okay.
Yeah. So if you go through those 30 practice questions, it will be similar type of question in the OP. Okay. Okay. Thank you then. Yeah. Thank you everyone.
Thank you so much, sir. It's been very
Thank you. Thank you, everyone. And
Thank you, sir.
Piyush, sir, I would like to add something. For the tomorrow Thursday session, please install the PG admin and the any Python ID.
Right.
Yeah, this is prerequisite for Thursday session, right?
Okay. And in OPP, will we have Python connection to database, or is it going to be only queries?
No. We have to connect to the database using Python.
Oh, but that will be through the portal only, right?
Yeah, portal only. Yeah.
Okay.
You can check the week 7 assignments are there, like programming assignment. Yeah. You have to type the code here in the editor only. Yeah. You can see.
Okay, sir. Okay.
And I would like to one thing, and please add Psychopagit 2 module. Please install Psychopagit 2 module in Python editor.
Yeah, you can go to the slide. Else we will explain in the next session. Don't worry. But if you watch the lecture, you have to install the Python ID or and Psychopagit 2 module. That is for connecting the PostgreSQL with using Python.
Okay.
Yeah.
Thank you.
Thank you, everyone.
Okay, thank you.
Hello.